Alright, hello class. In this video we're going to finish our discussion on conservative vector fields. There's a little bit more to talk about, but now that we've done a lot of the heavy lifting in the last video, we can actually talk a little bit more about what it is that conservative vector fields give us, and it's really important. So let's start though by finding or looking at an example of finding phi, the potential function, in a three-dimensional problem, just so you see that. It's essentially the same process, we just have a couple more steps, and after that we will start talking about the fundamental theorem of line integrals. Alright, so let's find the potential function, if it exists, of the following vector field. Let's say capital F is 9y plus 2z plus x cubed, comma 9x plus 5z minus 1/2 y, comma 2x plus 5y plus z to the 8th. Alright, so the first thing we've got to do, though, is we need to check to make sure this field is conservative. So to do that, I'm going to set up my little box here. And instead of putting the whole partial derivative, I'm just going to put x, y, z. Okay. And all right. So of course, the f sub x, g sub y, and h sub z we don't really need to mess with. And now we're going to check the other one. So g sub x, well, g sub x will be 9. Okay, plus 0 minus 0. Okay, then h sub x, let me use a different color here. H sub x will be 2. F sub y, well, f sub y will be 9. Okay, so those two match. Awesome. Then h sub y, let me use a different color there. H sub y will be 5. Okay, now here we'll do f sub z. Well, f sub z is 2. And those match across the diagonal. And then the final one will be g sub z, and g sub z is 5. And those match across the diagonal. So capital F here is conservative. Okay, so that means there exists a phi such that phi sub x equals our little f, 9y plus 2z plus x cubed. Phi sub y equals 9x plus 5z minus 1/2 y. So phi sub y equals our g. And phi sub z equals 2x plus 5y plus z to the 8th. I apologize, there's sort of a storm brewing outside, so if you hear thunder and whatnot, apologize if you find that distracting. I'll try and work around it best I can. Anyway, from here now, we can start on any of these, and I don't think any of them are really going to be much more complicated than the other. Right? It's not that like that crazy one we saw with the e's. So we'll start here with the phi sub x, and we'll integrate with respect to x. All right, so the integral of phi sub x dx is equal to the integral of 9y plus 2z plus x cubed dx. So this step, I understand if you don't want to write every single time, because eventually we get to the phi is equal to, and now we are right now we are integrating this with respect to x, and remember in this case the y and z are the constants. So y, z constants. Okay, so the integral will be 9yz plus, whoops, sorry, 9yx plus 2zx plus 1/4 x to the 4th, and then plus, I'm going to call this arbitrary constant of y and z, because those are our constants right now. Okay? Then we're going to take the derivative with respect to the next variable. Okay, so it's always integral derivative, integral derivative, integral derivative. So now I'm going to differentiate with respect to y and see what we get. So we're going to get 9x plus, with respect to y, this whole thing goes to 0. Okay, plus, and respect to y, this whole thing goes to 0. So then we get, now the derivative of this function with respect to y will be k sub y of yz. Okay, so now I'm going to compare this with this. Okay, so we have that 9x plus k sub y of y comma z, okay, is equal to 9x, let me match the colors here, 9x plus 5z minus 1/2 y. Okay, so the 9x's cancel, and that gives us that k sub y of yz is 5z minus 1/2 y. Okay, so what we're going to do is now integrate with respect to y. So it's like we integrate with respect to x, differentiate with respect to y, integrate with respect to y. Right, because the integral of ky of y comma z dy should be equal to the integral of 5z minus 1/2 y dy. So we get that k of yz is equal to, well, now we're integrating with respect to y. So here it's the z that's the constant. Okay, so we get 5yz minus, this will just be y squared. Then plus, now it can be an arbitrary constant, we'll say d of z. So z is the constant. So like I said, it's the same process, we just have way more steps to do. Right, so if we take this k of yz that we just found and plug it back into our phi, okay, we get a new phi that's equal to, I'm going to reorder this a little bit, it'll be 9xy plus 2xz plus 1/4 x to the 4th, and plus what we got here for our k. So 5yz minus y squared plus d of z. Okay, and now we are going to, like we've done in the past, differentiate with respect to z, our final variable, and then compare it to this phi sub z. Okay, so now we'll take the derivative with respect to z. Well, with respect to z, the 9xy goes to 0. 2xz becomes 2x. The plus 1/4 x to the 4th becomes plus 0. The plus 5yz becomes plus 5y. The minus y squared becomes 0. And the d of z becomes d prime of z. All right, so what we're going to do is take this and compare it up here to our other phi sub z. Okay, so what we have is that 2x plus 5y plus d prime of z needs to equal this guy, 2x plus 5y plus z to the 8th. Okay, so this right here was our little h, and this is what we found. Okay, so we're comparing what we found to our little h. And thankfully, everything cancels, and we get that d prime of z is equal to z to the 8th. Okay, now we integrate with respect to z to get that the integral of d prime z dz is equal to the integral of z to the 8th dz. And so we get d of z is equal to 1/9 z to the 9th plus an arbitrary constant. And then we can finally plug this guy back into, this d of z to get our final phi, right? Our final phi of xy. And so you might notice the way I always do this, when I get to the final phi, I always make it phi of xy. So phi of xy will be 9xy plus 2xz plus 1/4 x to the 4th plus 5yz minus y squared plus, and now we're replacing the d of z with 1/9 z to the 9th plus c, and there we go. There's our final potential function. Okay, I'll leave it up to you to check the gradient and see if it lines up with our original f, but with that example out of the way, I say it's time to move on to the other really important thing about conservative vector fields. Alright, so the big thing here is that conservative vector fields are what's called path independent. And that's what we were talking about before in the previous lesson, was that if f is conservative, okay, and let's say C1 and C2 are paths that have the same starting point and ending point, then their circulation, okay, is the same over those paths. So the line integral of f dot t ds over C1 will be the same as the circulation over C2. All right, so in other words, if we have a conservative vector field, right, and we have a path going from A to B, so this is C1, and a path C2 going from A to B, the circulation will be the same provided the field is conservative. So that means that, you know, we can go from A to B in any way we want. Okay. However, what that means in practice is that if it doesn't matter, then we could always just use the line. Okay? Since if the field is conservative, it will be path. Alright, now this path independence idea brings us to the fundamental theorem of line integrals. Now, this should remind you of the fundamental theorem of calculus just by its name. So a couple of things. Anytime you hear the fundamental theorem of whatever, it's usually a really big deal in whatever field you're learning about. So for the fundamental theorem of calculus, what it did was it had a theorem that connected integrals to derivatives, right? Or specifically definite integrals to derivatives, or definite integrals to antiderivatives, etc. So what the fundamental theorem of line integrals does, it's actually a very similar theorem to the fundamental theorem of calculus, and we'll get into that. So let's just take a look at what this theorem says. But the thing to remember about this is the path independence theorem. Okay, that's essentially what this is giving us, path independence. Okay, so let capital F be a continuous vector field on an open region R. Then there exists a potential function phi with the gradient phi equal to capital F if and only if. So in other words, capital F is conservative if and only if the line integral over C of f dot t ds, so the circulation, is equal to phi of b minus phi of a for all points A and B in R and all piecewise smooth oriented curves from A to B. Okay, there's a lot going on here, but to simplify things, first of all, I'll note that the book uses this notation for circulation, d vector r instead of tds. That's fine. That's going to simplify what we're talking about just a little bit. I want to start with that. So what is this saying? Well, what I want to focus on is that, one, what it's saying is that we can take any points in the region where the vector field is continuous, okay? Any point A and B, and any path between them that is piecewise smooth. So this is what piecewise smooth means, that it might not be completely smooth, but we can break it into a finite number of smooth pieces, okay? And what we're basically saying is that the circulation along any of these paths is just going to be phi of B minus phi of A. Okay? Provided we can find the phi. And this is true for any point, any 2 points. Okay? That is a really powerful result. Here's what I want to compare it to, though. Okay, so let's compare this to the normal fundamental theorem of calculus, the FTC, which says that if f is continuous on an interval a to b, then the and we need to close this off. Okay, if it's continuous on the interval from a to b, then the integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F of x is an antiderivative of little f of x. In other words, capital F prime is equal to little f. Okay? Another way to write this, and another way to think about this, okay, is in terms of the derivative. So we can instead say that if f prime of x is continuous on the interval a to b, then the definite integral from a to b of f prime of x dx is equal to f of b minus f of a. I posit that the fundamental theorem of line integrals is essentially saying the same thing. So the fundamental theorem of line integrals is basically saying that if the vector field f is continuous, then the line integral over C of f dot dr is phi of b minus phi of a, where phi is the potential function of f. Okay? In other words, the gradient of phi is equal to capital F. Well, that's exactly what this is saying up here, right? That if f is continuous, then the definite integral ends up being capital F of b minus capital F of a. Capital F is the antiderivative of little f, i.e. capital F prime is equal to little f. Phi is equivalent to the antiderivative of capital F, right? So phi is analogous to this same idea. It's basically the antiderivative. So the potential function of a vector field is essentially the antiderivative. Or equivalently, okay, if the gradient of phi is continuous, then the line integral over c of the gradient of phi dot dr is phi of b minus phi of a. We're saying the same thing. The gradient is analogous to the derivative. Now, we've mentioned that before, right? We use the gradient to help us find critical points by setting equal to 0. There are lots of ways we've already seen that the gradient is analogous to the derivative, say our f prime, okay, in multiple dimensions, and this is just another way that it is. Now, what I haven't said specifically, this is where C is basically any path going from A to B, okay? Any path, as long as it's piecewise smooth, okay? Well, how does this help us? Well, there are a few ways where it does, okay? Okay, so yes, the fundamental theorem of line integrals is interesting, right? It's a nice way to bridge this concept of one-dimensional definite integrals to, say, vector fields. But what does it actually give us? How does it actually help us? So, for example, say we want to find the circulation of f, which is the vector field 2xy plus z squared, comma x squared, comma 2xz, over c, which is the vector valued function 3 cosine t, comma 4 cosine t, comma 5 sine t, from t ranging from 0 to 2 pi. Okay. Let's say we wanted to do this without knowing the fundamental theorem of line integrals. Okay, so let's say without the fundamental theorem of line integrals, we would do it the long way. Okay, so to find the circulation, we need a couple of things. We need f of r. Okay, well, f of r, that's going to be f of 3 cosine t, 4 cosine t, and 5 sine t. Okay, so we're going to make x 3 cosine t, y 4 cosine t, and z 5 sine t. Okay, so our 2xy, well, that's going to be 2 times 4 cosine t times 3 cosine t. So it will be 24 cosine squared t plus z squared, and I can already see I'm going to need a little more room. Okay, now plus z squared, that will be plus 25 sine squared t. And notice we are 1 away from being able to get rid of this, right? There's nothing we could factor out of this to make this go to like 25 or 24. All right, so we're a little out of luck there. Then we'll have comma x squared, so that'll be 9 cosine squared t, and then 2xz. So 2xz, that will be 2 times 3 cosine t times 5 sine t. So that'll be 15 times 2, so that'll be 30 cosine t sine t. Okay, then we need to find r prime. Well, r prime, that will be negative 3 sine t, negative 4 sine t, and 5 cosine t. And then we get the fun property here, or the fun step of taking the dot product of these two, right? The f of r dotted with r prime, and you can hopefully see where this is kind of gross, right? So we'll have the 3 sine t times 24 cosine squared t. Okay, so it'll be negative 72 cosine squared t sine t. Then, just so we're clear what's going on here, these two are multiplying together. Okay, so then it will be negative 75 sine cubed t. Okay, then we're going to multiply these two together. So that's going to be negative 36 cosine squared t sine t. And then we're going to multiply these two pieces together. So we will get plus 150 cosine squared t sine t. All right, if I've done this right, we get down to, I think it's 42 cosine squared t sine t minus 75 sine cubed t. Okay, so hopefully you can already start to see, you know, why this is going to be nasty. Okay, so when we integrate this, the circulation of f dot dr is going to be the integral from 0 to 2 pi of 42 cosine squared t sine t minus 75 sine cubed t. All right, or, okay, so we can do it this way, or from the fundamental theorem of line integrals, I could check to see if f is conservative. Okay, so let's see. Here's our f. Let's set up our little table here to check if it's conservative. We'll have our little f, little g, little h, x, y, and z. And again, we will ignore we will ignore the main diagonal, right? The f sub x, the g sub y, and the h sub z. Okay, so instead, we'll look at g sub x. Well, g sub x is 2x, and h of x is 2z. Okay, f sub y, well, f sub y is going to be 2x, and the plus z squared goes to 0. So these match. Okay, then g sub y we can ignore. Then h sub y is 0. Okay, then we'll do f sub z. Well, f sub z is 2z. So there we go. And then finally g sub z, well, g sub z will be 0. So f is conservative. Okay, that means that the circulation over C of f dot dr is going to be phi of B minus phi of A. Okay, now where do we get that? B and A, that's the starting point and ending point. So our R, if we remember, okay, it was 3 cosine t, comma 4 cosine t, comma 5 sine t, t going from 0 to 2 pi. Now you might think, well, God, this is going to be terrible because now I have to find the phi. Actually, we don't. Check this out. R of 0, well, cosine of 0 is 1, so that'll be 3, 4, 0, right? And R of 2 pi is going to be the same thing. It's going to be 3, 4, 0. So the starting point and ending point is the same. This would be so, or let me write it like this. So A will be the point 3, 4, 0, and the point B will be 3, 4, 0, meaning that our integral over C will be phi of 340 minus phi of 340. I don't care what phi is. Those are the same. So our integral is going to come out to be 0. Now if we go back to here, we could probably do quite a bit of work to get down to 0 here. Okay, we would use our Pythagorean identity here and go through it like we normally would with, say, a Cal 2 problem. So let me go ahead and just write that out. I want to skip to the end just to, I don't want to focus on this. I just want to show that we get the same thing. Okay, it actually wasn't that bad because when we use the Pythagorean identity, we can then go to a u substitution. And when we do the u substitution, when we plug in 0 and 2 pi into our u, we get the integral from 1 to 1 of a bunch of stuff. Doesn't matter, it comes out to be 0. Okay, I don't know about you, but this may not seem that bad, but in my opinion, doing it this way is much nicer. It's much quicker, it's much cleaner, and this is my method whenever I see something really nasty looking and I have to take the line integral. I think maybe it's conservative, right? If the field is conservative, then maybe there's a lot less work we need to do. Alright, this also gives us a really nice property that if f is conservative and c is a closed curve, i.e. b and a are the same, right? It has the same starting point as it does ending point. That means always, in this case, that the integral of f dot dr over this c will be f of b minus, sorry, phi of b minus phi of a, but they're the same, so we get 0. That is huge. That, if you ever see that you're trying to find a line integral over a closed curve and the vector field looks like it might be conservative, it's always a good idea to just check to see if it's conservative, because if so, you're going to get 0 out. Okay, for example, let's find the circulation of capital F equals x cubed comma y cubed over the curve r equals 1 plus sine t comma cosine t. Okay, this is like an odd function here. It's a circle, but it goes in a different order and it's strange. However, it's going from 0 to 2 pi. This is going to be a closed curve because r of 0 is going to be the vector 1, 1, and r of 2 pi is also going to be the vector 1, 1. Okay, so I want to check if f is conservative. So consider that little f sub y is 0, right? Because if this is our little f and this is our little g, f sub y is 0 and g sub x is 0. Okay, so capital F is conservative and C is a closed curve. So, by the fundamental theorem of line integrals, okay, we have that the circulation of f over c, or the line integral of c of f dot dr, is going to be phi. Well, actually, forget that. It's going to be 0, right? Because it's going to be phi of 1, 1 minus phi of 1, 1. All right? So we don't even need to calculate what phi is. We know it exists because f is conservative. We know c is a closed curve. Therefore, we go straight to, well, the line integral has got to be 0. Okay, and also, what's nice about this is if we tried to do this the long way, right? So if we instead Right, so if instead we did this number here where we let, we found our f of r, right, which would be f of 1 plus sine t, comma cosine t, we'd get the vector 1 plus sine t cubed, comma cosine cubed t. And then if we found r prime, we would get the vector cosine t, comma negative sine t. Okay, and so f of r dotted with r prime, well, that's going to be 1 plus sine t all cubed times cosine t minus sine t times cosine cubed t. Now, this isn't impossible, okay? It's just going to be a real pain to get through. All right, I'm not, because you can foil, not foil, but we can expand this out and we can actually probably get down to something that's doable, but not friendly. All right, now here's an example where I definitely would not really, well, let me not say that. Let's take a look at this example, and I want to use the fundamental theorem of line integrals to help us out. But we can also take a look at what will happen if we don't. So let's look at what happens when we don't use the fundamental theorem of line integrals. So let's say we want to find the circulation of f, which is y cosine of xy, comma x cosine of xy, over the line segment from 0, 0 to 2, comma pi over 4. So without the fundamental theorem of line integrals, okay, we would first need to find f of r. Well, r, for a line segment, remember, is going to be x naught plus delta xt, comma y naught plus delta yt. And t will go from 0 to 1. So our r, well, thankfully our x naught and y naught are both 0, 0, so it's really just how much did we move from 0, 0 to 2, comma pi over 4. So it's going to be 2t, comma pi over 4t, and t is going to range from 0 to 1. Okay, so our f of r, well, that's going to be plugging 2t, comma pi fourths t into our vector field here. Okay, so we're going to put in 2t for x and pi over 4t for y. So we'll have the vector pi over 4t cosine of these two things multiplied together. So it would be pi over 2 t squared. Okay, comma our x, which will be 2t, cosine of pi over 2 t squared. Okay, then we need to find our r prime, which thankfully will just be 2 comma pi over 4. All right, and we're going to take the dot product, which will end up, when we multiply these together, pi over 2 t cosine of pi over 2 t squared plus, and then once again we're going to get pi over 2 t times cosine of, whoops, let me clean this up a little bit, times cosine of pi over 2 t squared, and look at that, those are like terms. Pi halves plus pi halves, the same thing, will end up being pi t cosine of pi over 2 t squared. All right, so the circulation is going to be, well, let me write the integral again. It's the integral over c of f dot dr, which we can now write as the integral from 0 to 1 pi t cosine pi over 2 t squared dt. Now this isn't terrible because we can actually set up a quick U substitution. Only because we have a t out here and a t squared in here. Okay, so for our quick U substitution, I'll leave the pi t there, and then the integral of cosine is sine of the stuff divided by the derivative of the stuff, which will be pi t, which cancels nicely. Okay, and we're going to be evaluating this from 0 to 1. Okay, so we'll get sine of pi over 2 minus sine of 0, so it comes out to just be 1. All right, so as we can see, this is not terrible. Okay, so this is without the fundamental theorem of line integrals. Okay, let's see what happens if we try and use the fundamental theorem of line integrals. Okay, so using the fundamental theorem of line integrals, first we need to check that f is conservative. Okay, so if this is our little f and this is our little g, f sub y, well, that's going to be a product rule, right? It will be cosine of xy left alone, because the derivative of y is 1, plus y left alone times the derivative of cosine, which will be negative sine of the stuff times the derivative of the stuff, which will be an x. Okay, then g sub x, same idea, right? Same exact idea. It's going to be derivative of x, which is 1, cosine xy, then minus, it will be the x left alone this time, then sine of xy, but now we're differentiating with respect to y, and we get, or sorry, we're differentiating with respect to x this time, and we get y on the outside. And notice that these are going to be the same, because this is cosine of xy minus xy sine of xy. I don't know why I keep trying to put a comma there. And this will be cosine of xy minus xy sine of xy. So since these are the same, f is conservative. So the line integral over c of f dot dr is going to be phi of 0, or not 0, 0, but phi of 2 comma pi over 4 minus phi of 0, 0. So now we just need to find phi. Okay, so to do so, we start with phi sub x equals little f. Right, so phi sub x equals y cosine of xy, and now we will integrate with respect to x. So integrating this with respect to x, thankfully, that y is just a constant. Okay, so our phi is going to be y, then the integral of cosine will be sine of xy divided by the derivative of xy with respect to x in this case, and that will be y. So the y's cancel, and we need to put a plus dy. Okay, so phi is sine of xy plus dy. Okay, now we're going to differentiate again with respect to y. I shouldn't say again because we haven't really differentiated yet, but we'll differentiate with respect to y, and then we are going to get cosine of xy times x this time plus d prime of y. And now we are going to compare what we got here up here to our original function. So our original g all the way up here And so we have that x cosine of xy plus d prime of y is equal to x cosine of xy. So these cancel, telling us that d prime of y is equal to 0, so d of y is simply just a constant, right? Now, thankfully, our phi, which is sine of xy, we don't need to put a plus c in here for the same reason that we don't do it with the normal fundamental theorem of calculus. Okay? So, this part here, so the integral of f dot dr is going to be phi of was 2 pi over 2 minus phi of 0, 0. So this will be sine of 2 times pi over, oh, sorry, it was pi over 4. Pi over 4 minus sine of 0 times 0. So this will be sine of pi over 2 minus 0, which will be 1. Okay, so as we see, either way we do it, we get the same thing. And really, I would say in this particular case, there's probably not an easier way. This, I think, exhibits the law of conservation of misery, which whichever way we decide to go here, it's going to be about the same amount of work. It's more about which direction you're more comfortable with. All right, so while that one may have been just as much work either way, this one, on the other hand, if you ever see something like this, so be on the lookout for this, where we want to find the line integral of the gradient of e to the xy dot dr, where c is the line segment from 0, 0 to 2, comma, natural log of 2. Don't even bother doing any extra work here, because we're already told that we have a conservative vector field, right? So by the fundamental theorem of line integrals, this is literally just going to be, well, this is the gradient of this. That's going to be e to the 2 times ln2 minus e to the 0 times 0. Right? Because this is our phi. So it will be a couple ways we can do this. I'm going to bring the 2 in. So I have e to the natural log of 2 squared minus 1. So this will be e to the ln 4 minus 1. So it'll be 4 minus 1, which is 3, and there we go. Okay, so cases like this, easy, right? You just invoke the fundamental theorem of line integrals. Anytime you have a closed curve, it's going to be super easy. Like the previous one we looked at would have been way quicker if that was a closed curve, because we could have just stopped right when we realized that f was conservative. Okay, I think that's enough for this particular lesson. So, what I do want to mention, though, is this idea we have is really nice. So the question becomes, is there any way we can extend it to our non-conservative vector fields, right? Because our liberal vector fields are still important, right? And there's no reason why we should exclude them at the expense of the conservative ones. So what we're going to be focusing on from now on is trying to get, or trying to look at a way to generalize this same idea, but for any vector field. Okay?